Hello everyone, let's take a look at the partial sum error. Now let's go ahead and take a look at an infinite series, the summation from n is equal to 1 to infinity of 1 over n to the fourth. And if we wanted to go ahead and expand that, we could write that as 1 plus 1 over 16 plus 1 over 81 plus dot dot dot. Now by the p-test, as p is equal to 4, we know that this infinite series will converge. But oftentimes we want to go ahead and determine what it's going to converge to. So we can ask that question. Now, in this particular case, we're not going to be able to find that. If this were, say, for example, an infinite geometric series, then we'd be able to tell what the actual series will, infinite series will equal to. But in this particular case, we don't know. So what we're going to do is we're going to rewrite our infinite series. Let's go ahead and take a look at how we'll rewrite that. Here's our infinite series here, and what I'm going to do is I'm going to break this up into two series. This is the summation from n is equal to 1 to k plus the summation from n is equal to k plus 1 to infinity. Now, it should be obvious that these two are exactly the same. It's just that this part right over here is going to be considered the partial series. And the reason why it's called a partial series is because it's only part of the infinite series. And then this part right over here is whatever is going to be remaining. Okay? And that is going to be called the error of the approximation, and this is going to be called, or the partial series is going to be called the approximation of the infinite series there. Now, I'm going to focus on the relationship, I'm going to solve for the error. Now, if I go ahead and solve for the error, I just have to subtract this particular summation from both sides of the equation, and I come up with this. Now, notice that what I have here is I have the sum minus the partial sum is going to be whatever the remainder is. Now there's going to be an important result that we want to go ahead and take a look at. It says if f is continuous, positive, and monotonic decreasing on the interval from k to infinity, and in this particular case what we're going to use is f of x is equal to 1 over x to the fourth, because of course that is what our sequence generator is going to be. The integral test will provide this important result regarding the error. So now we're taking a look at this error value here. It's going to say that the integral from k plus 1 to infinity of f of x d of x is less than the error, is less than the integral from k to infinity of f of x d of x. Okay, now let's go ahead and take a look at this. This is all of a sudden kind of coming out of nowhere. So let's take a look at why this is actually true. Okay, so notice that this inequality here is just rewritten here, and it's going to be associated with this particular graph. Here's k plus 1, k plus 2. These are the values of our sequence, and of course this is the function that goes to those particular values as well. Now, if I go ahead and take a look at the lower sum, okay, now r sub k, remember now this is going to be called the remainder, is going to be equal to a sub k plus 1 plus a sub k plus 2 plus dot dot dot. So here is a sub k plus 1 right here, and it's going to be represented by that rectangle there, which is bounded by the upper red dotted line. Okay, and then a sub k plus 2 is going to be this particular rectangle, again bounded by that upper red dotted line. Now what you should notice then is that if we go ahead and take the integral from k to infinity of x d of x, that's that. Notice that this part right over here is always going to be less than that, because of course we're talking about the lower sum. So we know that the remainder is actually going to be less than the integral from k to infinity of f of x d of x, which is the part right here that we have of our result. Now if I go ahead and do the same logic regarding the upper sum, where a sub k plus 1 plus a sub k plus 2 is going to be now the green rectangle, and of course I only have one green rectangle here, but I think people can continue with that pattern. We know that this is actually going to be greater than the integral from k plus 1 to infinity of f of x d of x, and here's that part right there. So notice that this is where this result is coming from. Now why is that result so important? That result is important is because we can use this result to determine how many terms are necessary for a specified degree of accuracy to approximate your infinite series. Now, let's go ahead and take a look at an example of that. It says, how many terms are necessary to approximate this infinite series that we have over here, correct to 6 decimal places? Now, if you wanted to, you could go ahead and keep on adding all of those terms and keep on going and keep on going and keep on going until you actually come up with this particular degree of accuracy. But if we go ahead and use this result, we can go ahead and find out what that value is, and we can then go ahead and also determine that that is going to be correct to 6 decimal places. So let's see how that works out. Now again, we need to first go ahead and check our conditions. Is f of x, which is 1 over x to the 4th, continuous, positive, and monotonic decreasing on k to infinity? And we know for a fact that that's going to be true. Now, I'm going to say that r sub k is going to be less than the integral from k to infinity of 1 over x to the 4th, because that's what that says. So what I'm going to do then is I'm going to go ahead and evaluate that improper integral. And what I come out with is that r sub k is going to be less than 1 over 3k to the 3rd. Now, being that I want this to be less than the amount of error that I can possibly have, which is going to be 6 decimal places. Now notice 6 decimal places is going to have 1, 2, 3, 4, 5, 6 zeros, and then 5 in the 7th place, decimal place. And then I know that r sub k also has to be less than 1 over 3k to the 3rd. And so if I go ahead and solve this inequality, I come up with k being greater than or equal to 88. So what that means then is that I need 88 terms in order to come up with an approximation of this infinite series with that specified degree of accuracy, because I know that the error is actually less than that. Okay, so let's go ahead and kind of summarize once more. The partial sum error is going to help us determine how to answer this type of question. In order to do that, we need to go ahead and take a look at our infinite series and change that form into a partial series, partial sum plus the error in the approximation, and then we're going to focus on the error of the approximation and relate it to that particular inequality statement. Okay, and then after that we can go ahead and, depending upon the question that's asked, determine how many terms are necessary for a specified degree of accuracy of our approximation to the infinite series. Okay, so we'll take a look at some questions that you might have regarding this particular lesson the next time that we meet in class. See you then. Bye-bye.